Okay, we're going to begin looking at some more complicated problems, and the pattern I probably you started seeing is whenever we have a new function, we learn how to find the derivative of that new function, and then we see how it applies when we have that mixed up with more than just that new function. That we have to use the old things that we use once in a while, and that is what would happen if we had what would happen if we had a product including the new function, that is a product of functions. Or what if we had a quotient, that is a fraction that included the new function? Or what if we had the new function inside parentheses along with other things and there was an exponent on it? We have to apply all those rules that we've learned before but incorporate what we've just learned. So here's an example of that. Okay, in this case, we're asked to find the derivative of y with respect to x. Oh, find that if y is x squared times natural log of x. And so, of course, I went through that ramble, and I'm hoping you recognize from that ramble that we really have a product here. We have the product of two different functions, x squared and natural log of x. So we can't take the derivative of either one of those separately. We have to use the product rule, okay? We have a product of functions. We have to use the product rule for finding derivatives. Product rule for finding derivatives. We can't learn something or partially learn something, then go on and forget about it later on. So remember how that goes. That if we have a function that is considered the product of two other functions, u times v, then the derivative of y with respect to x, we're assuming this variable is x, is the first function times the derivative of the second, plus the second function times the derivative of the first. And although I'm writing using v's, I'm saying first and second because that's really the way we need to think. So specifically for our function, we're asked to find the derivative of y with respect to x, and the first function here is x squared. Okay, so it's the first function times the derivative of the second function. And you may recognize right away that that's 1 over x, so we don't have to write that stuff. But I'm writing it because it might not be something we can always do in our head. Now it's the second function. The second function is natural log of x times the derivative of the first, the derivative of x squared. Now once we have that written down, we just go in and do the simple derivatives that we can. So we have an x squared times derivative of natural log of x is just 1 over x. And here we have a natural log of x, and the derivative of x squared is just 2x. Okay. Now, we're going to notice that in the first case, x squared times 1 over x is x squared over x. And let me also tell you that in the second case, we prefer to write it as 2x times natural log of x. See, if we write it as natural log of x times 2x, we might think that that's a 2x squared, but it's not. See, we might get confused and mix up what we're taking the natural log of with the derivative. And so if we put that derivative result in front, it will be clear that we don't have those two things mixed up. And in the case of x squared over x, that's just x, isn't it? So that would be x plus 2x times natural log of x. And it's not necessary, but you might notice that x is a common factor here. So we factor out an x, we'd have a 1 in the first place and a 2 natural log x in the second place. So that's another way we could write this. You know, this is certainly okay with me. Some people might write that, or some books might write that. Okay, let's move to the next page for our next problem. Okay, we're given the function y is equal to the natural log of x times x squared plus 1, the quantity squared. And we're to find derivative of y with respect to x. Now, if we just jump right into this, we use the chain rule version of finding derivatives of logarithms. You know, which because we're not taking just the natural log of x. So the chain rule, remember, would tell us to find this derivative. What we have to do is say 1 over the argument. So it's 1 over all that stuff inside, x times x squared plus 1 squared. And then we have to multiply that with the derivative of what's inside. So the derivative of x times x squared plus 1 squared. Now, what I would tell you is to find this next derivative is going to be a big lot of work, okay? It's a lot of work because we have a product, don't we? X times that stuff squared. So we've got to use the product rule. Inside the product rule, we're going to have to take the derivative of the second function. And the second function is parentheses with the power, so we have to use the general power rule on that. It's a lot of work to find this derivative. That's a lot of work. And sometimes that's what we're stuck with, okay? Sometimes we're stuck with that and we have no choice. But if we invest the time to learn, and I make a big point there, if you really are interested in learning, then you can make your life easier in some cases. If we use laws of logarithms before we get started, use laws of logarithms on the original function before we find the derivative, not after we started finding the derivative. So on y equal natural log of x times x squared plus 2, plus 1 being squared. If we take that function and apply laws of logarithms, we'll get something easier to deal with. So here's what I mean. I'm going to rewrite the whole thing down here. Y is equal to natural log of x times x squared plus 1 squared. And what I'm needing you to concentrate on right now is that this is a product between x and that squared stuff. So law number 1 that we listed in laws of logarithms would tell us that we can write this as y equal the natural log of the first factor times natural log of the second factor. Oops, not times, plus, my bad. Okay, the logarithm of a product is the sum of logarithms. Now, in the first case, log of x is as simple as we can get. But in the second case, we have the logarithm of something that's being squared. That is, the whole argument is being squared, isn't it? That exponent up here is what I'm looking at. So that exponent can be brought down in front of the logarithm. Now, unfortunately, we can't simplify any further because that square is not on the argument. It's only on part of the argument. And it has to be on the whole argument to bring it down and put it in front. And this plus sign keeps us from breaking that apart, doesn't it? Because we don't know how to deal with a logarithm of things that are being added or subtracted. So right now, this is as simple as possible. But it's better, it's better than what we had the logarithm of before. The whole purpose is each of our arguments is simpler now. So when we go and find derivatives, we won't have to work as hard. So now we just simplified the function. Now we find the derivative of y with respect to x. And so that says, well, what are we going to do? We're going to take the derivative of the first function, which is just natural log of x, and we're going to add to that the derivative of the second function, which is 2 times natural log of x squared plus 1. Now, in the first case, the natural log of x is just 1 over x, isn't it? In the second case, we have that 2 that's being multiplied with the function. And so we really have 2 times the derivative of the natural log of x squared. The natural log of, derivative of the natural log of x squared plus 1. Now, to find that derivative, Here's our 2 out here. To find that derivative, we say 1 over the argument, x squared plus 1, and then we multiply that with the derivative of x squared plus 1, which really isn't a whole lot of work. The most work we're doing is just writing. So we end up with the 1 over x in front. We have a 2 times a 1 over x squared plus 1, and then, of course, the derivative of x squared plus 1 is simply a 2x. So we have the 1 over x here, and plus, now, I'm not going to write this, but I guess I am going to write it over here. Remember, 2 we can think of as 2 over 1. So we're really multiplying the 2 as a numerator, and we're doing the same with the 2x. So we have a 2 times 1 times a 2x, or a 4x numerator, and an x squared plus 1 denominator. And not that that was real easy, but it was something that we could accomplish. Now, that was easier than taking that other derivative up there, wasn't it? Now, one thing that you might notice is that we could still add these 2 fractions together. And once in a while, when you're trying to match an answer, what if your answer was just a single fraction? See, what if your answer, if you looked it in the back of the book, or you were looking on My Math Lab, or you're looking at some other resource, and you got an answer that looked like this. See, over here on the side, you got that answer, you'd think, man, I must have done something wrong. And that happens once in a while, that you think, well, how in the world did they come up with that answer? Well, all that took place is these 2 fractions are added together. See, what we need to add these fractions together is a lowest common denominator, don't we? And in this case, that lowest common denominator is just x times x squared plus 1. And so that means in the first fraction, we've got to multiply both the numerator and the denominator by x squared plus 1. So we've got to multiply on top and bottom. See, we're just multiplying by 1. Now, in the second fraction, we've got to multiply on top with an x and on bottom with an x, so that we get x times x squared plus 1 on the bottom. Now, when we look at that, let's see. This first fraction has an x squared plus 1 on top and an x times x squared plus 1 on bottom. And the second fraction has a 4x squared on top and an x over x squared plus 1 on bottom. And of course, we recognize that when we add those numerators together, we're going to have an x squared and a 4x squared added together. So we're going to have a 5x squared plus the 1 that's also there on top, and x times x squared plus 1 on bottom. So be careful. This is really the better answer, and we might have stopped right up here, which probably we should not have. Okay, let's go to the next page for the last problem in this part, and it's about finding the equation of a tangent line. Okay, here's the problem. Determine the equation of the tangent line to the graph of y equal natural log of x divided by x at x equal 1. Now recognize the natural log of x, the x that's there is inside natural logarithm. It can't cancel with an x on bottom. We have to apply natural log of x before we can do a division. So no cancellation here, no simplifying here. Now, we need a point that is on the line, and of course that's the point of tangency, isn't it, that we can use. And that point of tangency has the x value of 1. So using the fact that x is 1, we can calculate y, because the point of tangency is not only on the tangent line but also on the graph. And so we would need to calculate the natural log of x, which is 1, divided by x, which is 1. So that's just the natural log of 1, isn't it? And then I hope we can remember without using our calculator that the natural log of 1 is 0. Because remember, here's what this means. If we have the natural log of, we'll say, x, okay, of x is equal to some number, means really what this is all about is that number that it is equal to is an exponent, and it's the exponent that goes on the understood base of e. So it means e to the n is equal to x. Well, what we're looking for, see, is e to what power is going to be 1. See, that's what we're looking for over here. When we say natural log of 1, well, the answer is a power. And what power do we put on e to get 1? Well, the power 0 is the exponent we put on e to get 1. And so that's the reason we have a 0 result there. And also just remember while we're here, because this may have gotten away from you, that the natural log of a negative is not allowed. That doesn't make sense, because that would say we could put an exponent on e and get a negative number, and we can't put an exponent on e and get a negative number. We'll always get a positive number. And the natural log of 0 is not allowed, because that would say we can find an exponent to put on e that would give us 0. E to what power would be 0? Well, e is just a number, and we can't put a power on a number that would give us a 0 result. So those two are not allowed. Okay. Now, the slope is the next thing we need, right? The slope of the tangent line. And of course, the way we calculate slope is that we find the derivative, and then we evaluate it at the x value, in this case, that we're interested in this case, that's 1. Okay, but to find the derivative, our function is a quotient. See, it's natural log of x over x. So when we're looking for a derivative like this, we have to use the quotient rule. Remember, if our function is a fraction, okay, our function is a fraction, then the derivative, the way we take the derivative of a fraction is we say, okay, denominator times derivative of numerator minus numerator times derivative of denominator, all divided by the denominator squared. Remember, that's called the quotient rule for derivatives. Not the quotient rule for logarithms, the quotient rule for derivatives. And we need to have that committed to memory, so we don't have to think about that. So here we go then. We're going to find the derivative of y with respect to x. And remember, we're looking way back up here. There's our function. So we say what? We say denominator, which is natural log of x, times derivative of numerator. Oops. I already started out wrong, didn't I? My bad. It's denominator, okay, which is x, times the derivative of the numerator, which is natural log of x, minus the numerator, minus the numerator, I had a senior moment there, times the derivative of the denominator. And the denominator, of course, is x. And then all of that is divided by the denominator squared. Well, the denominator is x, and so that's what we have to square. Okay, one more time since I goofed that up so badly. Remember how the derivative goes. It's denominator times derivative of numerator. So that's the x times derivative natural log x, minus the numerator times derivative of denominator. So that's the natural log times derivative of x, all divided by the whole denominator squared. Okay. So the derivative of y with respect to x, now we're actually going to start calculating those pieces. So we have an x, and the derivative of natural log x is 1 over x, isn't it? Minus a natural log x, and the derivative of x is just 1. So natural log of x times 1 is just natural log of x. And that's all over x squared. So in the first case, we have what? Derivative of y with respect to x is x times 1 over x is 1, minus 1 times natural log of x is just natural log of x, and that's all over x squared. Now, recall the purpose of this is really just to find the slope of the tangent line. So we take this information to find the slope. That's what we're really trying to do, is we take the derivative and we evaluate it at x equal 1. So in this case, we put a 1 in for the x's, and it would look like this, wouldn't it? And when we do our calculations, let's just remember that natural log of 1, we just discussed, natural log of 1 is 0, and 1 squared is 1, so we end up having 1 over 1, don't we? Which is just 1. So in this case, the slope is 1. Now, what we could do here then, next is that we'll come up with the equation. And to come up with the equation, of course, we use y minus y sub 1 is equal to n times x minus x sub 1. And our y sub 1 is the y0 of our point of tangency, the y value of our point of tangency, and we calculated that to be 0 up above. And our slope, of course, is 1, x minus the x value of our point of tangency, and that was 1. That was given to us. And so we end up with what? Y on the left side and just x minus 1 on the right side. So there's the equation of the tangent line. Now, before I stop here, what I would like to do is to just point something out, because this can be useful in the future. Since I don't see you in the classroom, this could be useful in the future. I don't particularly like the quotient rule because it's so complicated, and you can see here I goofed it up when I started, and I know it. So I don't particularly like to use the quotient rule, and if I can get away without using it, sometimes I do. And so what I want to point out to you in this case, you can always do this, but in this case, we could have written our function as x to the negative 1 times the natural log of x. That's actually the same thing, isn't it? Because x to the negative 1 is just 1 over x. And if we did this, then we could use the product rule instead of. See, we can use the product rule rather than the quotient rule. And sometimes I find that easier. Sometimes maybe it's not particularly easier. Maybe in this case it really wouldn't be. But it's something to keep in mind in the future. Well, that's the end of this part. So I don't know if I'm going to have another part or not. We'll just see.